Action.
Second order differential equation PDEs are many. Few among them are the Laplace's equation, the Newton-Heath equations, and also the Poisson equation, and many others. Second order partial differential equations are pertinent, are key in solving engineering problems. Sequel to this, the heat conduction equation is expressed as partial t, function of x comma t, with respect to partial t, the time. Now, this is equal to second partial derivative of t with respect x-axis. But of course, a constant must be induced because of the factor, the conductivity, the variation in the area, and also the humidity that affects the temperature and also other factors for conductivity flow. So hence, the heating equation becomes partial t, function of x comma t, respect time is equal to partial squared t, function of s comma t, respect x squared. Now, this partial squared t, partial s squared is also written as nabla square. Nabla squared t is also equal to partial squared t, function of x comma t, respect partial x squared. So that as a relationship, the general expression for heat conduction equation with respect to constant will now be partial t, function of x comma t, respect the time is equal to alpha square, assuming alpha square is a constant variable, multiplied by partial squared t, function of x comma t, respect x squared. Of course, this can be written too as partial t, function of x comma t, divided by partial t is equal to alpha square nabla square function of t of s comma t variables. This precisely is the heat conduction equation, and it is highly relevant in solving advanced problems and heat modeling challenges. However, we have another pertinent equation which is also referred to as the wave equation, and the wave equation is partial square t, function of s comma t, respect partial t squared, which connotes acceleration, while in its equation this also connotes velocity, is equal to alpha squared nabla square t, function of s comma t. Note that this is for one-dimensional plane, that is the x-plane. And the x-plane for functions of several variables is one-dimensional plane system. Of course, this one-dimensional plane system can go beyond a scope of variability to give diverse plane, which is functions of multivariables, and that is the essence of partial differential equation, whereby the heat conduction equation and the wave equation can simply be written as partial t, function of s comma t, respect t is equal to alpha squared into partial square of t respect x axis direction plus partial square t respect y axis direction plus partial square t respect z axis direction of the second order. Now, this is three-dimensional heat conduction equation. Three-dimensional heat conduction equation. Now, oftentimes, one-dimensional plane system is what is applied in engineering. That is to say, where partial square t, partial y squared, plus partial square t, partial z squared is equal to 0. When it's equal to 0, hence, the general relationship now gives you partial t. In fact, you can also reverse it, but we could make it otherwise directly as partial t, function of x comma t, respect t the time domain is equal to alpha squared partial square t partial x squared. This is the derivation of three-dimensional plane to first-dimensional plane when the y-axis direction is 0 and the z-axis direction is 0. We now have a one-dimensional plane. And of course, this is more pertinent in application in engineering. Now, also same for the relationship on wave equation. Wave equation connoted as partial square t partial t squared is equal to alpha squared partial square t partial x squared plus partial square t partial y squared plus partial square t partial z squared. Of course, it is a constant that goes into them. When the whole of this gives 0, when it's 0, then we now have partial square t partial t squared equal to alpha partial square t alpha square partial square t partial x squared, a one-dimensional plane. This is often used as wave equation. Wave equation. And the wave equation is key in advanced engineering mathematics. So we now look at the Laplace's model. Now, if this is heat conduction equation for this heat equation, we now have the Laplace's equation, not Laplace transform. The Laplace transform that we know is quite different, which is Laplace function of t is the integral 0 to infinity of function of t exponent minus st dt. This is not what we are talking about when we mention Laplace. It is spelled same, not this. In Laplace's equation model, it is connoted on a three-dimensional plane as partial square t respect partial x squared plus partial square t respect partial y squared plus partial square t respect partial z squared is equal to 0. And of course, this can be called nabla square of t function of x, y, z equal to 0. Also, in some quarters or in some books, it implies t subscript xx function of x, y, t rather z plus t of y subscript into x, y, z plus finally t of subscript z function of x, y, z equal to 0. Now del is also called nabla, also called the vector operator, and the symbol is nabla. So these are pertinent in partial differential equation as an introduction. Of course, it will not be left out the implication that exists when variables on the right hand side exist, and that goes to talk about Poisson equation. And the Poisson equation is connoted as nabla square of function of t s, y, z equal to functions of three variable s, y, z. In all of this, these are general connotations that exist in partial differential equation. So it is pertinent to have the view of the second order differential equation from the application perspective, where we have the heat equation, which has just been written here in full form with a constant which is partial t respect t is equal to alpha square partial square t partial x square. That is one-dimensional plane heat conduction equation. This is a summary of what has been exegised. The exegesis of this concept has been thrown at this point here. So, but this is a reflection of the summary view of it. Heat conduction equation, then while the wave equation simply is partial square t respect time domain squared is equal to a constant squared partial square t partial x squared. Take note the difference, this second order partial derivative with respect to time, first order derivative with respect to time for heat conduction equation, and this is wave equation. So lastly is a Laplace's equation which is modeled as partial square of t respect s squared plus partial square of t respect y squared plus partial square of t respect z squared equal to 0. Laplace's. So the Laplace's equation that you see has nothing to do with the general Laplace transform. The general Laplace transform, like I reflected initially, that is called Laplace transformation, which is integral O to infinity function of t multiplied by exponent minus st differential t. It is not what we are talking about. Of course, they are related. They are cousins that did great work in engineering mathematics. So this is not what we are referring to. No. But rather, this is the Laplace's equation we are talking about. Laplace's. So Laplace equation is different from Laplace transform. Take note. So that is it.